Good evening, ngBeer. Cheers. It's important to have beer on ngBeer. So let's do some together. Okay, so tonight I want to take you on a journey to discover the realms of virtual scrolling. We will talk about theoretical stuff, like how is it working internally, how like different implementation styles, native ones or with JavaScript implementations. We will compare performance analysis to finally reach our goal to have high performance lists in Angular. So before I go into the details of virtual scrolling, let's talk about our typical lists, like what we do on our daily basis. Think about like you build, for example, a SaaS application where just people, your clients, can put in to-dos. It's the most simple example I could come up with. And it works fine in the beginning. People add more stuff. Your company grows, your clients grow, they enter more and more data, and suddenly they will call you with a frustrating message like, the app is not behaving like it did before, it's slow, sometimes it crashes, especially on those low devices, applications will crash, and you want to go and inspect the reasons. So first of all, how do we implement those simple lists? Of course, we use ngFor and iterate over our stuff and just render items like we just used to do. So you open up the dev tools because your client called and everything's crashing, and you see what the actual, you have 26,000 DOM nodes just to render this freaking list. It has 500 items, by the way. So it shouldn't be too much, but yeah, you see 26,000 DOM nodes, it's a lot. And that is actually a problem, and the problem is too much DOM. So why is it a problem? Because you have the browser render pipeline, which has 5 major key stages where the browser is analyzing your code, interpreting it, and executing it. In a stage of 5 areas, so you have scripting, that is your JavaScript code that's executed. There you might maybe like put style changes, add class, or whatever. So your browser has to recalculate styles, or you add DOM nodes. Your browser has to layout. You lay out a node which has a border color, so it has to paint, and then you have maybe something that is on a different layer, and then your browser has to composite again. So those are the 5 stages, and with too much DOM, you actually put work in all of those stages for the browser to do, and you don't want that. We will discover later, but let me say your web vitals will suffer. The core web vitals, on the one hand, LCP and INP, so for interactivity and loading performance, and of course, total blocking time is suffering if you just render too many items at once. So let's talk about performance analysis of those simple lists. And before we go into the details of the performance analysis, because you will see a bunch of those in the next couple of minutes, and I will inspect 3 different aspects. So first is bootstrap performance. So when you just initially enter a route or display something in a dropdown or something. So you bootstrap an application or just a component. Then you have interaction performance, like you do something with it. You check a checkbox, or you want to enlarge a text or something. And then you have scroll performance, because scroll performance is important for virtual scrolling aspect. So let's talk about the bootstrap performance of our native list. 500 items are rendered. This is unthrottled, and I forgot to mention, most of the examples I will show you are like with throttling enabled on my machine, because we also care about those slow devices, and this machine is definitely faster than any of the mobile phones. Yeah, so that's why we throttle the CPU to see what mobile clients would also see, and this is very important. But this example is unthrottled, rendering 500 items, and we see 1.5 seconds until a list is visible when you bootstrap it. This is extremely brutal. We see 1 second scripting time and another 500 milliseconds of rendering time. So 2 stages are affected here. We have the scripting stage and the rendering. It is like putting together, recalculating styles and layout. So those 2 stages are heavily affected here. What about interaction performance? On interaction performance, we see not too much scripting, because there's not too much scripting involved. If you just hit the checkbox, there's not much you need to recalculate, but the browser has to do a lot of stuff, as you can see. You still see long tasks about like 300 milliseconds, and I will show you off in a demo what the simple interaction is. But you see like heavy recalculating styles, heavy layouting tasks, heavy paint phases. What about scrolling performance? On the top bar, we didn't see it before. Here, this one. there you see the actual frame rate, like how much milliseconds does your browser need to calculate one frame for your application. And in this case, it's peaking at 120 milliseconds. This is brutal. You can never, ever achieve 60 FPS or even 30 FPS with it. It's impossible. So let's go to a quick live demo and show you the actual problem in a live environment, or like, let's say close to live, it's localhost, but it's good enough. So here I have a beautiful demo application. Let me close the performance monitor for now. Or actually, we can keep it open so we see the problem immediately. So we have actually no DOM nodes visible here. Let me zoom in, maybe. I think we should see everything at this size. That should be good. So let me navigate here to this. I want to zoom in here. I want to zoom in actually here on the, yes, on that one. Perfect. Oh, let me navigate here to the default route, which opens this 500 items. I just clicked there, I clicked and moved away. You see, DOM nodes are kicking off. We have now 26,000 DOM nodes. And from the visual aspects, like, it's not that complex of an application. There's some buttons here to do something, but basically just text, an image, a checkbox. So this is brutal, and you can maybe even tell by just watching how I'm scrolling that it's, but we can for sure just close the performance monitor and just do a recording of it. So let's scroll around our list here a bit with the performance recorder. Let's also do some interactions here, and this is unthrottled now, so I didn't even throttle my CPU. Still, we should see, yes, that's what we see here. We see heavy long tasks are kicking in. Didn't record screenshots. That's very unfortunate. Otherwise, I could show. But here is like where the interaction happened, and you see like 50 milliseconds only for like I'm clicking a checkbox. That cannot be right. It's a problem. We should fix that. So if I turn on throttling, I mean, we're on a meetup. I have time, so I can just repeat it here. So let's do another inspection here and scroll a little bit in the list and also hit the checkbox here. Perfect. I should have recorded screenshots now. Absolutely beautiful. So here we see our interaction on the screenshot. And now we can tell by taking a look here in our DevTools. Let's make this a little bit smaller. Scroll up here. Here's our interaction, so the click event, and here you see like 500 milliseconds. I just clicked the checkbox. 500 milliseconds cannot be true. So this is definitely a thing we need to take a look at. And now let's go and talk about what we can do about it. First a sip of beer. So let me quickly introduce myself. I'm Julian Jandl. Hi. I'm performance engineer at the company Push-Based. Thank you. Thank you. Yeah, don't want to talk any further about me. I'm performance engineer, and I want to talk a little bit about performance improvements in the next couple of minutes. So virtual scrolling to the rescue. But before we talk about JavaScript implementations, let's talk about like the theoretical aspects of virtual scrolling. So we have, I hope it is large enough for everyone to see. Last rows, is it fine? Yeah, great. So we have three main aspects that make up for virtual scrolling is in a theoretical concept. You have a runway, which is basically the area where you put all the items. It should be the same height of all the items you want to render as a whole. Maybe you want to render 10,000 items. They have fixed 50 pixels each, so you have 500,000 pixels for the whole list. This will be your runway. So determining the scroll bar so that it is nicely sized. Then you have the viewport, that is the actual visual part of the application that contains the items that should be currently visible on the viewport. Plus, like, this is common sense for all of the implementations. You have kind of an overflow on top and below. So you have a smooth feeling when you scroll up and down because you just render some items on top and below. This is the overflow. When I'm talking about overflow, just some items to have smooth scrolling. And then you have like the scroll event, which determines which items should be visible. So you scroll down to the middle of your container, then of course you should render the items that should be in the middle of the container and nothing else. All the other items should be just virtual items. So this is the general concept behind it. And now I want to tell you about native virtual scrolling. It's like in double quotes because I call it native scrolling. It's not the actual official naming for it, but I think it's worth naming it like this. So this is coming with the CSS containment API. There's a special rule, just a one-liner, content visibility auto, which will make items disappear when they are not in viewport. The browser does it for you. So let's go into detail on this rule. So for everyone who's already familiar with the CSS content containment API, knows about paint containment and layout containment. It basically makes sure that if you apply it on an element, on some node, it is completely, entirely shielded. You tell the browser, you do not need to relayout this node if anything else was relayouted. I am responsible for the layout, so please don't do it. So you just save the browser somewhere. It is doing layout containment, paint containment, and on top of it, it will skip rendering, like as display none would do, all nodes that are not part of the actual viewport. So if we apply this, what benefits do we gain? For our bootstrap performance, now we see the same pattern again, like as I did with the very native list implementation. For our bootstrap performance, this means 90% of rendering work is simply gone. Like the browser does not have to do the work to lay out all the nodes that are like far down in the viewport, like the items that are not the first 10 or something, and it just skips it. So we have an improvement of 90% in rendering time here. Still, we have 1.1 seconds until the list is visible, and this is like unthrottled with my device with its full power, and it's even plugged in, so should behave good. What does it mean for our interaction performance? We see the same thing again, like all of the rendering tasks, recalculating styles, layouting, and paint is like reduced by 80%. This is really good without doing anything but just applying one simple CSS rule. What about our scroll performance? Well, scroll performance, as you can tell from the frame rate here, it's still peaking out at, I don't know, 130 milliseconds, so still very bad frame rate. So it's kind of equal performance to the one we've seen before. But what does that mean? Let's take a look at how the application is behaving now with this rule applied. So I want to fresh start. I want to close the DevTools right now. Fresh start. Let's refresh completely. Very good. And now you see I'm going to the route content visibility here. And like from the visuals, of course, nothing has changed. But when I start scrolling now, you should see already like white areas appearing here. It will be way more visible if I just open the performance tools and enable throttling, close them a little bit, and then let's scroll. So you see like those white areas appearing here all across the board. And this is just the browser doing its native virtual scrolling things. So I applied the CSS rule here. Take a look. There we go. Maybe I should turn off throttling now because otherwise my system is dying entirely. Amazing. This is the container. And there we see now this tiny little CSS rule, content visibility auto, and you can confirm that this is working by just going in your elements panel, scroll to some element that is not visible at all, select it. Yes, here you see. Here's the hint. Very small. I'm sorry for the, especially for the descendants are skipped due to content visibility. So browser's actually telling you it's skipping the rendering work. So this is how you can confirm your rule appliance is working. Downside is if I do not specify any height here, if I remove that, my scroll bar will completely, like, you will see that the scroll bar is jumping around because the browser doesn't know the height. So if you do not specify any dimensions for the element and the element goes out of the viewport, the browser thinks this element has 0 height and it collapses entirely. So you have to specify dimensions if you want to use that. It's a really neat and cool trick. Came with the latest updates, and I think it is definitely worth mentioning in a virtual scrolling talk. But that's what why I showing off. So let's recap. What can we achieve with the native APIs? So as we have seen, it doesn't help with scripting, because how could it? It's just a CSS rule. It only skips rendering. It does not skip creation of elements. And this is where we need to think about like what we are doing. When we just render diffs in a loop, it's cool. If we render actual components, like think about a table, or like my to-do list example, which has like event listeners and buttons and a local state and whatever. It's not skipped by the browser, of course not, because the JavaScript is executed, the browser is not rendering it. So if you rendering components, of course, memory consumption is still a problem. Of course, event listeners is still a problem. It's just the DOM that's not there. So it helps for interaction. It does not help for Bootstrap, and especially not for scripting. Also, browser support is something. It is supported everywhere besides Safari. Like Firefox has it with a flag now. It will support it soon. Apple just said they will come up with their own solution, which will work better than content visibility, so they don't support it. So yeah, if you rely on Safari, you cannot just use it, and you cannot, or they will support it. It's like, yeah, Apple stuff. So finally, what about JavaScript implementation? Because we had ngBeer, we have to talk about JavaScript, right? Let's keep in mind our theoretical concept from before. We have the runway, we have the viewport, we have the rendered rows, we have the overflow, and all of this has to be baked into JavaScript now, into some form of algorithm. And I want to dive deep into two different implementation concepts you can go there, because there's like those are the most used concepts I know of, in the wild. And there's the transform elements container. This is like implemented by the CDK virtual scrolling. If you ever applied that or used that, this is the technique they are using behind the scenes. And then there's transform elements, and this is like used by, for example, Twitter or by WhatsApp or by other chat clients you may have used. And spoiler alert, also by RX Angular. And I want to go into detail about that as well. So let's talk about the first theoretical concept, transform elements containers. With this approach, you basically want to have one container that you just move across the runway. You have one container that's containing all the views you want to render for the specific scroll position, and just move this container up and down in your viewport and replace the elements within it. That's the trick behind it. So let's dive into how does it work. We have 3 steps here. Render the runway, so make sure the thing has the proper height, so the scroll bar has the correct size. Second step is we want to render the actually currently visible elements, because otherwise we show something but not the one that the user wants to see. And third step is position the container. So we filled our container with items, then we need to position it to our actual position. As our inputs, we of course need to know the viewport size. We need to be aware of it. Either we ask the DOM about how large is like our viewport, or we get it as an input, or we need it as an input. We have the number of items, of course. If you want to render 100,000 items, we know it up front, so we can properly size our runway. We need, for this example, a fixed row height, because with dynamic or auto size, it would be way too complex to go over the implementation details. So let's go with fixed size at the moment. So we know each row, the dimensions of each row. And of course, we know the current scroll position of the user. So the user scrolling, we can attach to the event and like ask for the current positions. So let's go step by step. First thing is we want to render the runway. This is extremely easy, especially for fixed size stuff. So we know the run height up front, let's say 50 pixels. And then we just calculate amount of items times row height, and that's the size of our runway. That's like the most easy task to do. Now it's getting more complex, and I don't want to overwhelm you with this slide. So let's go step by step. On the left side, you see all the inputs. On the right side, you see the calculation. So let's go from left to right. So you see, let's go here, overflow size. Let's say we want to render 2 items as an overflow on top and below. So we know overflow is like twice the size of an element on top and below. Then we have scroll top. That's the actual scroll position of our container. Currently, the user is scrolling. Like we scroll around and then we just measure the scroll top, the current position. Then we have the row height, which is also fixed in our scenario. And finally, we have our viewport. Viewport is the thing that is currently visible for the user and should actually display the rows we want to display. So let's talk about how do we calculate stuff. First, we need to know what is the first item we want to render. First item is really easy. We just pick like our scroll top position and divide it by the row height. Of course, we need to account for the overflow. Like here, start is scroll top divided by row height, and this is like you can do or you can omit it, but for completion, I put it here as well. Same goes for figuring out what is the last row we want to actually render. We have the size of our viewport, we divide it by our row height, and then we also have to account for the overflow. And the final piece that is missing here is just this simple for loop here. So we have our start, we have our end. We just say, okay, from start to end, render all the views. So now we have one container which has all our elements rendered, which we want to render. We need to position it. That's the final task. So we just need to have our offset value. We calculate it just by having our start value, multiplying it by the row height, and then we can transform our container down to the position where we actually want it to have. Useful side information, we use translate transform y here, this one. Because doing it with absolute position and positioning it like with top, for example, would cause layout. This one is not causing layout. This one is only working on the GPU. Like if your device has a dedicated GPU or has hardware acceleration enabled, then the browser will be faster when you do translate versus positioning with top positions. So how does this one look in the DOM? In the DOM, it is the complete opposite. It's the other way around. So the topmost, the outer container will be your actual viewport. Then inside of the viewport, and now it's getting a little bit tricky, we see here this CDK virtual scroll spacer. So this one, this single div lying inside of the viewport is actually determining the size of our runway. So you just hack it by saying, okay, it has a height of, I don't know, 1 billion pixels, then it stretches all across and will raise the container size and will display the correct size scroll bar. So that's why it is here. And then finally, you see the elements container here, containing all of our items. We see 1, 2, 3, 4, what is it? 10 items or something rendered, and it is transformed to the position by using translate. So this is how CDK is looking internally. How do you use it? Maybe you have used it before. It's like part of the Angular components package. It's CDK virtual scroll viewport as the outer element. So this looks like really like the DOM was looking before. You specify an item size. You'd use, instead of ngFor, CDK virtual for, and that's it. You achieve virtual scrolling. So let's do performance analysis and take a look at how this is actually behaving in our application. So again, Bootstrap performance as the first metric we want to inspect. We see enormous gains here in scripting time. Minus 75% is like extremely good. This is this is with CPU throttling enabled, by the way. So even with a very slow device, it's behaving quite decent, I'd say. It's still too much. We can improve. I will show you later, but it's really good improvement. Rendering time also decreased by 80%. Of course, we render less DOM, so browser has less stuff to do. So this is a really good improvement. Then let's talk about interaction performance. Interaction performance is like absolutely amazing. You cannot say anything about it. 25 milliseconds for interaction is beautiful. You cannot improve further, in my opinion. Scroll performance. Yeah, scroll performance. What should I say? It looks a little bit not cool. Like we have a bunch of scripting time here. You see long tasks all over the place, 500 milliseconds blocking time. It sounds awful. Let's see how it behaves. Let's go to our live demo. Can I have a fresh? Oh, I need to close DevTools and I need to refresh. I'm sorry, but my demo has memory leaks, so I want to have a fresh start. Yeah. We are a performance-focused company, by the way. Okay, so this is Rx Angular. I didn't want to go to Rx Angular. I wanted to go to CDK. Yes, CDK virtual scroll. Perfect. So this is how CDK virtual scrolling looks like, and like you can immediately tell by like watching me clicking this compared to the other experience where I could do a whole micro talk in between, that this is behaving much better than before. So actually beautiful. Let's take a look at the DOM implementation so that you trust me and that I didn't lie to you. So let's scroll here. I'm scrolling now, and as you can see, the scroll position, like it's not updating every time I'm scrolling. It's just waiting for some threshold to move the container, which contains all the elements, up and down. So I'm scrolling a little bit down, and there you can see like the whole container is just moved across the board. So here we have the viewport. Inside of it, we have the wrapper, which holds all the elements. And finally, we have here in the very bottom, the spacer. If you can read the number here, it has so many zeros, I cannot even tell you the number, how large it is, but it has many zeros. Let's check performance really quickly, because I told you it looks awful, and I want to show you what this means. Wrong button, I'm sorry. I need to throttle first. Throttle my CPU. Start the recording, and now you will see what I mean. So I'm stabilizing the scroll position, and you have to wait like, I don't know, half a second until the white screen turns into something that you can actually consume as a user. So this is how it looks like in the frame chart. You can actually see a second. Nice. So yeah, what this means is I'm scrolling around. The algorithm is just waiting for me to stabilize the scroll position finally. And then it starts calculating, like, okay, what do I need to do? What views do I need to destroy? What views do I need to cache? Which views do I need to put where? Recalculate the position the container, and this is what's happening here. It's taking, like, on this device, a second just to give me an updated viewport. And I mean, we actually gained benefits here, because even with my still throttled device, I can just easily interact with the page without it feeling extremely sluggish. I can just scroll around. It's like, it feels okay. It's cool. So we have a benefit here, but still we have to wait like a decent amount of time until something is visible. And this is like the actual promoted, recommended go-to way of using virtual scrolling in Angular. And like, I felt we need improvements here, right? So let's take a look at what we can do. So recap from the CDK virtual scrolling. It still struggles with a little bit with bootstrap time, as we can see, like 400 milliseconds is not like the words ending, but still also not cool. And it also struggles a lot with aggressive scroll behavior. Like if you, like me, aggressively scroll this list, you see like how the scripting task is still messing up your browser, and how the users still suffer because like this is bad interaction timing. The actual bad INP timing is 500 milliseconds, I guess, and like at 500 milliseconds, the browser or the crux will actually tell you have to improve with, otherwise like you have just a bad metric. So there's definitely room for improvement here. So let's talk about the final approach for tonight, the transform items. It is very similar to the concept before, but now, as you can maybe tell from here, you do not have a wrapper container around anymore. Instead, you just transform each item individually. Like every item gets its single own, absolutely positioned spot in the viewport. This is the general idea behind it. So how does this work? We have now, this is the most important difference, I think. We have not 3 steps, we have only 2 steps. And this is very important. We have to position and render the items individually. So render an item and position it. Stop. Render an item and position it. Stop. So this is the difference. Before it was render, 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 position. Now we have render end position, render end position, render end position. That's the difference here. We have the same inputs as before. So also, not surprising, calculating the runway, so the total amount of items showing the scroll bar is also the very same as before. So amount of items times draw height is resulting in the whole runway size. Again, the chart from before, with a slight difference. On that side is completely the same. We have still this, the scroll position, we have the overflow, we have the row height, and the viewport size, of course. This is also the very same. We just want to know what is the first item we want to render, what is the last item we want to render, and then here we have our difference. We have the same for loop from start to end, but now calculate for the very item you're just iterating over, its position, apply it, and then move on with the loop. That's the difference. So in the end, you just have like for each item a dedicated offset value and a dedicated translation, like where it should be. And of course, again, we use the translate in over the position absolute and top value because we want to run the task on the GPU. If you have hardware acceleration, your browser will definitely thank you for that. So how does this look in the DOM? It's quite similar to the one we've seen before. Like we also have the head here with like sizing our runway with a hacked element that is basically just oversized. But we thought it would be a cool idea to not use height. Instead, we also use translate here, which gives us again the advantage to run tasks on the GPU instead of forcing layout. Other than that, you see each item individually has one absolute position with a translate value just assigned to it. And by the way, if you go to your Twitter feed, you can do it like in the next break or something. Open the DevTools, take a look at the runway. You will see this exact pattern. This is like, and I thought Twitter would be the best virtual scrolling experience I've ever seen in any web app. So it has to be for a reason, right? And now it's time to finally introduce RX Angular virtual scrolling. So where we tried to bake in all those concepts to make a very beautiful virtual scrolling experience. So how do you use it in the DOM? It's basically the same as the CDK one. You just replace the CDK with RX and you're good to go. You have a viewport. You have, instead of ngFor, now RX Virtual 4, and you render your items. And before we go into any performance analysis, as we did before, I need to do a slight sidetrack and talk about the concurrent mode, because this is something very special to RX Angular and which makes most of our performance improvements so good. It's the concurrent mode. So concurrent mode means basically we try to split up long tasks into small tasks and render them one by one, chunk by chunk by chunk. So this is what you see, and if we do performance analysis of our very first example, where we just rendered the ngFor list, this is actually what you see in the flame charts. Like you have to click to navigate somewhere, then ngZone will kick off tick, we see detect changes, and then ngFor is kicking in and doing detect changes for all of our views, like 500 views, 500 times detect changes. The longer detect changes takes, the longer will be your task in a whole. You can't do much about it. So our approach was, why not take all of those like tiny detect changes calls and like split them? We can if we want. So we take them and split them and render them one by one by one, giving the browser time to react to user input, to render something, to display something. So basically, if that one here is your new route that is being displayed, your INP will be here instead of here. And that's amazing. So you can do, like, you can replace ngFor with RX4. This is already existing. You can just use it and it will do just this. You can, if you inspect flame charts, you will just see this. And we tried to marry the views, the virtual scrolling techniques with our concurrent mode and build a new virtual scrolling experience for Angular. And now let's go into performance analysis. So what does it bring us? And as you can see, look at it, 100 milliseconds. Yeah, I'm sorry. I'm too excited now. I'm switching to German already. Like, it is throttled. It is throttled, 100 milliseconds. Throttled. Before we still had like 500 milliseconds. It's like so good. I cannot even tell you how good it is. And also, here you see all the chunks. Perform work until deadline. Perform work until deadline. Perform work until deadline. Those are like your individual items that are rendered. Interaction performance, very same, no improvement. It was amazing before, it is still amazing. Scroll performance. I don't have to say, oh boy, because there's no long task, no blocking time, nothing. We have only 200 milliseconds until we see the next view is displayed, because we do not have to show all of them. We just have to show one. It's so good. So let's go into a live demo and take a look how this looks. Close this. I know memory leaks, I'm sorry. Okay. I want to show you with throttled because then you can tell how amazing it is. Can I even show it like this? Maybe I need to do, yeah, perfect. Let's go to that rod here. Did you see it? Like, tuck, 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 tuck. The rows were like just inserted one by one. And let's do it again, maybe with the recording so we can actually see the visuals. Yeah, beautiful. So can we do that again? And can we close that one? Oh, it was already closed, so we have to enlarge it. Yes, and that's what we have seen before. So we have here our click task doing whatever the click task is doing. Here is INP now. So there is INP now. Before, INP had to be like here because it had to render all the other views as well. And here you see like the individual chunks. And if I scroll over the screenshots here, you see like how the views are entering the screen bit by bit. So this is how Bootstrap performance is actually improved. Now let's also see how scrolling performance is actually improved. Don't want to skip throttling. Close this, start the recording, and just do a tiny movement here. Wait for something stabilized. And here we can turn off. Here's the scroll movement. Here the scroll event kicked off. And here our first view will be visible. So this is like, I'm not sure if you can read it. Wait, summary will tell us. And then everybody can see it. Summary will tell us eventually. Yeah, 140 minutes. 144 milliseconds. Absolutely beautiful. Before we had 500 milliseconds. Or even a second if you have seen it. So this is like the magic behind the virtual scrolling, having them translated one by one. And I forgot to show how it looks in the DOM, of course. Let's go here and attach it to the other side. Take a look at the items. There you go. You see here, translate Y, and this like, I don't know, super crazy number because we scrolled down so much, and this is like 30,000 items. So this is why this item, this number is so crazy. Let's zoom, sorry, out a bit so that we can see more items and see what is actually happening here. Okay, I didn't want to do that. Okay, perfect. So now we see all of our items here that are just here in the viewport will just be updated with their transformed values when you just scroll around the list here. So this is what's happening in the transform item technique, and the transform container would just transform the whole container thing up and down. Okay, so let's also do a recap for this one. So we kind of did a compromise with scripting here. We're not telling that we fix all of your scripting issues, because we don't. We just split them and execute them one by one. That is the whole idea. So we basically do a compromise with the browser in like, please render something, give the user some feedback that is something happened, and do the rest like later on. This is the whole trick behind it. And a couple of more things until I'm actually done. Angular was designed to be a drop-in replacement. So if you ever plan to replace your CDK virtual scrolling thing with RX virtual viewport, then you really just have to change CDK to RX, and that's it. You're good to go. You have different view scrolling strategies. Like, we now talked only about fixed size stuff. There are more complex scenarios for example, auto size strategy. It is experimental. It's also on our package experimental. But we came up with the idea of dynamic sizes. So what about like views where you have like different rows that are different sized, but you know them up front? For example, a row that has just a additional description, and you know additional description will always be 50 pixels tall. So you can say what row with additional description has 50, the other 100. That's it. That's the whole idea of the strategy. So you don't have to let the browser actually read the DOM and automatically calculating it and giving it more room to breathe. The key advantages, because we didn't talk about it, of the transform item stuff is you have in total less rendering. The browser has to do less layout stuff, because inside of the elements container from the CDK, you have to insert rows, you have to move rows, you have to delete rows, and it's causing layout for the browser. If everything is absolutely positioned, it's not calculating, it's not causing layout for the container. It's only causing layout for one single item. Also, this approach actually made it even possible to use our concurrent rendering approach, because otherwise it wouldn't be possible to talk to each and every individual view and position it on the viewport. It's making it much more easy to work with it. Yeah, final live demo where I just want to show off all the different scroll strategies. So you see here on the left side, RX Angular, dynamic size, auto size. I guess what I really want to show off is the auto size thing, because that's what we are most proud of, because the CDK one is actually deprecated because it cannot support scroll index and it cannot support scroll to. Like, if you have ever used CDK virtual scroll thing, auto size strategy, it's impossible to use scroll to API. It's impossible to determine the scroll position, like to determine the index of the item that is currently scrolled. So for in this example, this one here would be the item that gives us the index for scroll position. In our example, though, as we know all the positions from all the items, you can actually see scroll index is returning something. And not only that, also scroll to, like, let's give it index 500, scroll to, it's working. I mean, it doesn't say 500, but it's working. And with that, before I wrap it up, I need to give credits, because Zuoma, if you know him, if you don't know him, please follow him, because he's such a great guy doing web performance stuff. He's advocate at for the web at Google. He writes cool stuff. He gave me the initial motivation to work on this virtual scrolling thing, because he wrote this beautiful article, Complexities of an Infinite Scroller, with a nice demo with code examples. Really helpful. So I have to give credit here. Please like our library, give it a star, follow us. And yeah, some words about Pushbase. We're a web performance consulting agency. We do performance stuff. We can consult you in any complex problems in your application. So please book us if you're interested. And finally, thanks for your time. Thanks for listening to me. And yeah, I had a blast speaking to you. Any questions?
How much faster is it compared to paper?
How much?
Yeah.
I don't know, like
Three times faster.
no more. It's
Three
like
times?
yeah, it's like INP will be 5 times faster, I guess. Yeah. Yeah, it's beautiful.
What is the open source library called again? I can download it.
Ah,
Where you can give it a star.
you mean that one?
Can I start it?
Yes, of course. You can start.
Should everybody else start it?
You know, like here is like a link.
Yeah. You can tell that they also have stake.
We not all we do not only have template improvements to improve performance, we also have state management solutions. So if you're interested, and they work perfectly together. Yeah.
Oh.
No questions?
What is the problem for auto sales strategy? Because I guess this is most advanced use case of the whole project, and is, as far as I understand, not really solved out there.
Yeah. So what's the problem for auto sizing? So there's a reason why. There's a reason why this is not working, the scroll to in the CDK implementation. Because they're not like they don't actually know the size of each element. They don't ask the browser to give it the size. Can we join the party? Instead, CDK is like guessing. It's a guessing game. That's why they cannot really tell you what scroll position you're currently at. And that is also the problem, because if you ask the DOM all the time, it's expensive. Like querying the DOM for layout critical APIs, for example, in this case, the size of an element, offset height or client height, or get bounding client rec.height, or whatever you want to have to determine dimensions, is a problem, because when you do it at a bad timing, you will cause a forced reflow, because your browser, in order to give you the right answer, has to do a re-layout before. So you ask the browser to give me the size, and it's not just giving you some size, it wants to give you the actual value. And if it knows, okay, right now it's like at the point in time your script is running, it's not accurate, I have to do layout now. And this is a forced reflow, and this is extremely bad and very expensive. And you will also see it here on like purposely made at that point in time. So let's go here in the auto size strategy, and you should see now that is like, first of all, it's actually beautiful. Second of all, yes, you see this here. This is a forced reflow now. Recalculate style and layout, like both next to each other within a scripting task. So this is always indicating that something is actually not right. In this case, we have to do it like that. And we want to do it like that because we want this calculation to be part of our work that's put in the scheduler. Otherwise, we would only schedule change detection, like updating the text or whatever, but not positioning of the item. That would mean we cannot control the length of the task that is happening afterwards. That would mean we cannot block blocking tasks. And we are doing it this way, that it is part of our actual scheduler, so we can account for it. So if this task is taking longer than 20 milliseconds, please do not do any other task here, because we want to let the browser interact after 20 milliseconds in order to achieve this 60 FPS frame rate. This is like the whole trick behind it.
What's the library name again?
Let's put it on screen and then there you go.
Let me start the library now on my phone.
Any other question?
More beer.
Yes.